Okay, so let's do OSPF intra-area routing. Now, the next topic we're going to learn of is, I think, inter-area. So we have intra-area. Means within an area. Within an area. Then we're also going to see inter-routing. Inter-routing is between areas. Between areas. And we're also going to see external routing, inter-area. Hey, happening between areas, inter-area routing. And you're going to see external routing. External ni between autonomous systems, between ASS. An autonomous system is like an ISP, as I explained. It's independent, uses their own routing policies, which are closely guided by their policies. Okay, so intra-area, within an area. We know that in OSPF, in order to cater for scalability, you can, when the routers increase in your network, you can create multiple areas so that you can reduce the size of the LSDBs and not overstrain the routers in calculating the SPTs and SPFs. Okay, so we want to see if you just have a single area, what kind of data is shared within that area. So that is what we want to see in this particular chapter. Excuse me. So this topic is about how OSPF calculates intra-area routes, including how intra-area routes, including how to use Router-LSAs and Network-LSAs to describe topologies and routes, and how to build the shortest path tree. So by the end of this chapter, you should be able to, Eric, please help us read this.
Be familiar with the Router-LSA contents and functions. Be familiar with the Network-LSA contents and functions. Yes. Understand the shortest path first algorithm.
Okay, thank you very much. So let's begin with what we call the Router-LSA. When we talked of the LSA header, we talked of something like, was it the LSA type or something? We talked of something like the LSA type, LSA type field or something. So we have several types of LSAs. Type 1 is called the Router-LSA. Remember, LSA is simply a link state advertisement. It's the one that carries summary information about networks, link state advertisement. Okay, and then we have type 2 LSAs. Type 2 LSAs are what we call the Network-LSA. Okay. So we also have type 3, type 4, type 5. We also have up to, I think, type 10 or something. But in this training, I think we're only going to go up to type 7 or something. So within an area, two types of link state advertisement are shared within an area. So only these two, type 1 LSAs and type 2 LSAs. That is the Router-LSA and the Network-LSA. Router-LSA is produced by each router in your network. So each router will produce a Router-LSA to describe the state of its links. Then we have the Network-LSA. This one is advertised by the DR, to describe the state of the network, something like that. Yeah. So we want to begin by diving deep into Router-LSA so that we can understand how it looks like and the fields that it has. Okay. Sorry. So as I have said, let me just do something here. Okay. So as I've said, each OSPF router in a network will originate, that is produce, a Router-LSA for each area to which the router belongs. So here for example, we have a point-to-point link between RTA and RTC. So RTA will produce a Router-LSA. Similarly, RTC will produce a Router-LSA for this area. If RTA was connected to another area, then it will also produce a Router-LSA for that area. Now, the Router-LSA has several fields which we must understand in detail. Excuse me. Now, if, for example, we are in RTA, whose router ID is 1.1.1, if you use the command display OSPF LSDB, display OSPF link state database router, so you're specifying that you want a Router-LSA. Self-originate, meaning that it is this router that has produced this particular LSA. So when you do that, you're going to get the details of the Router-LSA of RTA. Now, the first part of the Router-LSA is the LSA header. Remember, we looked at the LSA header fields. So the very first field on the LSA header is the LSA type. So this one will specify type 1, meaning it's a Router-LSA. Then the link state ID. The link state ID really is supposed to describe the interface via which that LSA has been advertised. But most of the time, it uses the router ID as the value for the link state ID. Then you have the advertising router, which is the router ID of the router that has generated that particular LSA. So 1.1.1.1. So that part is what we call the header, the LSA header. Then the second part here is now what we call the the data. So this is the data that this particular LSA is actually carrying. So we must also understand the fields that are here. Now, a Router-LSA is used to describe multiple links that are connected to that particular router, directly connected to that particular router. So it uses several fields to do that. One of them is the link ID. Let me check that. So for example, here we have the link ID. So the link ID is the router ID of the neighbor router. So for example, this data is for router 3. Then for the data is the IP address of the router interface that has advertised the LSA. So in this particular case, it is this particular link here that has advertised. Remember, this LSA, this Router-LSA is for RTA. So for the data, it will be that. So it simply means that this particular interface is connected to router 3, simply put. Then the next thing is the link type. Now, I need to dive a little bit deeper on the link type because it's important. Now, the link type should not be confused with the OSPF network types. So, link type in Router-LSA, link state advertisement. Now, you can have 3 types of links. So we have 2, we have point-to-point. Number 2, we have what we call a transnet. Transnet. Number 3, we have what we call a stabnet. So you must understand these 3 link types. Simply put, point-to-point means that particular link has only been connected to one other router. Yeah. So it has only been connected to one other router. That link has only been connected to one other router. So that is what we call a point-to-point link. Point-to-point link. Point-to-point link is normally treated as a topology information, meaning knowing that that link has been connected to only one other router, it means that we can be able to tell the topology of that particular network. So it's treated as topology information. Then we have transnet. Transnet, I think trans comes from the word transit. So it simply means that that particular link has been connected to a transit network. So it means 2 or more routers are attached to a broadcast network, or to a broadcast network, or to NBMA, to an NBMA network. So you see, for example, here it is P2P because this link has only been connected to one other router directly using a serial cable. So it's a point-to-point link type. But if we had connected them, for example, using an Ethernet cable, then because that is a broadcast network, then the link type will be transnet. If we had connected them over virtual circuits, fully meshed FR, then the link type will be transnet. Okay, I hope you've understood that. Then the last one here is the stabnet. This is a link to a stub network. Most of the time, when you talk about stub network, we are talking of a network that is an end. It's the end of the network. So no other connection can be made from that network to another network. It's the end of the network. It's the end. That's what we call a stub. So the end of something. So a good example that is used to simulate, for example, a stub is a loopback. When you create a loopback interface, it's not like you're going to connect that loopback interface to any other interface, to any other network. It's an end. So that's what we call a stubnet. So the link, for example, the link of a loopback interface will always show the stubnet under the link type. So I hope that is clear. So those are the 3 link types that are supported when it comes to Router-LSAs. Now, the last thing here is the metric. Excuse me. The metric. So the metric here is simply the cost for that interface. So in this case, the metric is 48. The metric is 48. And as I've said, the metric is simply the cost. So you see, that particular data can be used to describe the topology information. Who you're connected to and on which link, and what kind of link type is it. So that's a topology information. Now, the second part is showing us the routing information. So let me just clear this so that now we can we can focus on this. Sorry.
Bye.
Hi. Yes, you have a question? Okay. So let's look at this routing information. So the first field here is the link ID. The link ID here is the IP address. Is the IP address of the stub network. And then the next thing we have here, so is the mask, the subnet mask of the stub network. And then we have the link type as the stubnet, because this is a stub network. And we have the cost, which is 48. So those are some of the details that we can see in this particular example. Let's move on to the next one. So this generally was used to describe the Router-LSA for a point-to-point interface. So let's look at the Router-LSA for a broadcast or non-NBMA interface, because they'll differ just a bit. So Router-LSA describing a broadcast or an NBMA interface. So as you can see, these particular routers have been connected over a shared medium. Now, for example, if we are in RTC and we use the command display OSPF LSDB router self-originate, so we will have the header just telling us the type of LSA. It's a Router-LSA, and the router that originated that particular LSA. Okay, then the next thing we get is the topology information. Now, I need to mention that. Let me just go back here. This topology information here, this routing information here is used to describe the network. Simply saying that the network ID is that and the mask is that. So using that. And the link type and the cost, something like that. So that is used to do that in a point-to-point network. So here, with the Router-LSA does not have routing information. It only has the topology information. So let's decipher the topology information here. The link ID is the interface IP address of the DR. So RTB with a router ID of 2.2.2 is our DR. So the link ID in a Router-LSA in broadcast, and that one is this particular, the address of that particular interface. Okay, then we have the data. Now the data is the IP address of the router interface that has originated this particular LSA. So this particular interface here. Now look at the link type. Remember we said whenever it's a broadcast or an NBMA, then the link type is going to be a transnet, and the metric means the same. So here the cost from this particular link 10.1.235.3 to the shared network is actually 1. So you can see here they're asking, where is the network ID on the subnet mask? So in broadcast and NBMA, the Router-LSA does not describe the network ID or the subnet mask. That is described using type 2 LSA, as we are going to see. So type 2 LSA is called the Network-LSA. Just give me a minute. Okay, by the way, I did not give a disclaimer to the new trainees here. I have a daughter and sometimes she'll be bumping in. Like now she's just woken up. Say good morning to my friends. Huh? And she's a terrible too. So I'm just trying to contain her. So just a minute, I hand her over. She just woke up and she wanted to say hi because she can hear me talking. Okay. Bye. I love you. I'm coming. Not scared. Okay, guys, can you hear me? Hello?
Yes, yes.
Okay, let's look at the network LSA, which now is the type 2 LSA. Now, the network LSA, it is important to note that the network LSA is only produced on broadcast and NBMA network. Network LSA is actually produced by the DR. So it's only on broadcast and NBMA where we have elections. So it is important to note that. So network LSA is used to describe all the routers that are attached to either a broadcast or an NBMA network with the interface of the designated router. So all the routers that have been connected to the DR. So network LSA is used to really to specify that. So let's look at the components of the type 2 LSA, network LSA. So for example, in that network that we just looked at, in that topology, RTB is the DR. So if we do display OSPF LSDB network self-originate, we can see that this is OSPF process 1 with router ID 2.2.2. We are on area 0, and this is the link state database. Okay. So the first part is the header. The first part is the header, the LSA header. So the type, the LSA type. So here it's going to indicate type 2. The LSID here indicates the interface IP address of the designated router. The interface IP address of the designated router. Then the advertising router is used to indicate the router ID of the DR. So that's the first part. Then the second part now is the information it carries. So this one carries the information. It carries the information about the network. It carries the information about the network. So number one, it shows the subnet mask of the network. So, for example, when you look at the routing table or the OSPF routing table, you'll see the network ID. So how it gets the network ID is by doing a logical AND between the IP address of the link and the mask. So I hope you remember that when we were learning IP addressing, we said that when you do a logical AND between an IP address and its mask, you get the network ID. Okay, so other than describing the network, it also goes ahead to describe all the attached routers. So a list of all routers connected to this network. So it starts with itself. Then I've also been connected to 3.3.3 and 5.5.5. 5.5.5.5. So those are the routers that they have been attached to on area 0. Remember, LSAs are specific for each area. Okay. So is there anything that I've not said? Okay, I think that is it. Let's move on. Now, LSDB in an OSPF area. Excuse me. The next SPF calculation. Okay. Now, at this point, I want to request you to use your phone and take a picture of this topology so that we can refer to it, because I don't want to be going back. So just take a picture of it with your phone, so that when I talk of RTA, RTB, RTC in the subsequent slides, you should be able to see it. Okay, for example, I've just taken mine, so good. I hope you've also taken a picture. Now, from RTA, if we are in RTA and we enter the command display OSPF link state database, LSDB, we can see that we have, is it 5? We have 5 type 1 LSAs, meaning that each router has produced an LSA. You can see that from the advertising router here, advertising router here. So you can see that from the advertising router column, that we have a router LSA type 1 from router 4, from router 2, from router 1, from router 5, and from router 3. And then the next bit is the network LSA. We have two network LSAs that have all originated from R2 or RTB. You can tell from the router ID here, 2.2.2.2. So why do we have in RTA, why do we have two? Why do we have two network LSAs? So if you look keenly on this topology, you'll see that RTA is connected to RTB via an Ethernet cable, meaning an election will occur, OSPF election will occur between these interfaces on RTB and RTA. So here, RTA and RTC have been connected using a serial cable, so no election will happen. Similarly, anywhere else we have serial, no election will happen. Now, the other place where an election is going to happen is between this area. So because they have been connected using a switch, we are going to have an election between RTC, RTE, and RTB. And again, RTB becomes the DR on that area. So that's why we are having two network LSAs here. So that's why we're having two network LSAs here. So I hope that is clear. If you look at the link state ID, you remember we said that the link state ID is on a network LSA is the IP address. The IP address of the link on the DR that produced that network LSA here. So you can see we have 10.1, .12.2. So that one is from this network here. So this guy is .2. So that one was produced. This one was produced from that interface. And this other one is 10.1.235. This one here, 235. That network .2. So this interface produced this Network-LSA. So I hope that is clear. You remember the age field on the LSA. So number of seconds since that LSA was generated. Length is the size in bytes. Then this sequence is the ID number of that message. Metric is the cost. Type is the type of LSA. So within an area, you can only get router LSA and network LSA. Router and network LSA. But if we don't have elections, you can only get router LSA. So I hope that is clear. Okay. Now, let's look at the shortest path first calculation. It uses the data from the router LSA and the network LSA. So we want to understand how, and it's important that we understand it. So type 1 and type 2 LSAs carry both topology information and routing information. Routing information is the network ID and the mask. And I've told you, once we have the mask, getting the network ID is simply doing a logical AND. Topology information is simply saying, I'm connected to this one, I'm connected to this one, I'm connected to this one, and this is the cost. So that is topology information. And we've actually seen them. Now, SPF, the shortest path first algorithm, occurs in two phases. So in the first phase, you create the shortest path tree, SPT. So create an SPT. You create an SPT on the basis of topology information in the router LSAs and network LSAs. So you create a shortest path tree, and then number two, you calculate an optimal route. An optimal route. I hope it's not one of you calling me. Someone is calling me and I'm wondering who. Can I be heard? Hello?
Yes.
Okay, thank you. Okay, let's move on. So let's see what really happens in each of those two phases. Okay, it's done in a number of steps. Excuse me. The very first step, so number one, the very first step involves the router checking its own router LSA. Now, when creating the SPT, shortest path tree, each router will assert itself, or each router will put itself as the root of the tree, as the root node. That's the word. So we want to see now how RTA is going to build up this particular tree with itself as the root. Are you seeing? So adding others until it gets to this next phase, which is now route calculation. But now the tree will look like this at the end. So we just want to understand how does it create this tree. So that is what we want to understand at this particular point. Okay. So the first thing it will do is to check its router LSA. So for example, in RTA, if we type display OSPF, LSDB router self-originate, we can be able to see details about other devices that this router has been connected to. So you see we have one there, and we have another one there, and we have a third one here. Now we have what we call here the candidate list. Candidate list. Now, for you to be added to the candidate list, or let me say this, how can I put this now? Stubnets cannot be added to the candidate list. Just a moment. Someone is really disturbing me here, so I'm thinking of just blocking them first so that I finish up this, then we can I can call them later. Okay, so stubnets cannot be added to the candidate list. The only links that can be added to the candidate list is the transnet and the point-to-point link types. But if you're a stubnet, for example, this link is simply used to describe the network. If you're a stubnet, you cannot be added. You cannot be added on the candidate list. So I hope that is clear. Now, the candidate list has 3 columns. The first one is the candidate. So here we're going to add these 2 candidates. The link that is connecting us to RTB and the one that is connecting us, I think, to router 3, RTC. So the first column here is candidate. It's simply used to describe the link ID. So link ID, the link ID. Then the next one is the cost. So we get the cost, the total cost, from the metric value. So for example, for that one is 1. Then we have this one here is 48. Then after that, we have the parent node. So at the very beginning, of course, the parent node is that particular router that is beginning to create this SPT. So the router ID of the parent node. So I hope that is clear. Now, of the 2, we look from the candidate list now, we look at the cost. We look at the cost and we add the candidate that has the lowest cost to the RPT. So here we are going to add this particular guy because this guy has the lowest cost. And if you look at our topology, the one I told you to take a photo of, actually this guy is the DR. RTB is the DR. And whoever advertised this is the DR. So they're going to be added on the SPT, but now they are going to be added as a pseudo node because they're a DR, as a virtual node. So that's why they're using a different color here. So next we are going to see that we are going to have a different color. Now, before we move on to the next, after being added to the SPT, your entry is deleted. Your entry is deleted from the candidate list. So I hope we've understood that. So let's move on to the next step. So the next thing is, because this guy is the DR, in our network, we are going to evaluate RTA. Router A is going to evaluate the network LSA that is produced by this DR. So that's the next step it's going to do. After checking its own router LSA, then it goes and checks the network LSA of the DR. So here, if we press display OSPF LSDB network 10.1.12.2, so we want to produce the network LSA that has been generated from that interface 10.1.1.12.2. Okay, so from there we have the LSA header here, we have the mask, but most importantly we have a list of attached routers. We have the list of attached routers. So these attached routers, they are going to be added on the candidate list, with the exemption of anyone that is already on the candidate, that is already on the RPT. So for example here, we are not going to add 1.1.1 because it's already on the RPT. So we're not going to add it on the candidate list. Remember 3.3, we are carrying it from the previous slide. Now we had already added it on the candidate list. Okay, so now the next thing, so here the only thing that is going to qualify for entry into the candidate list is the 2.2.2 network. So after that, we look at the cost. So the cost here is going to be the parent cost, which is 1, plus the cost of the DR, which is 0. Anytime you're connected to the DR, which is a virtual node, then your cost is going to be 0 because it's a non-existent router. The DR is simply a non-existent router. It's simply a virtual. So the cost from the DR is 0. So that's why here we are having 1 plus 0. So the parent, then the DR, so we get the cost. Then the parent node is the DR, which is on 10.1.12.2. So again, we're going to compare these costs. So we compare these costs. Which one has a smaller cost? The one that has a smaller cost is this one, which has a cost of 1. So that one that has a smaller cost is added on the RTP. So we add this particular router on the RTP 2.2.2.2. Remember, it's the same router because RTB is the DR, but the DR is treated as a virtual node. So it's like they're separate. So I hope you understand that. Okay, so let's move on and look at the next one. So on step number 3, so of course now we are here. In the previous slide we were here. So we now check the router. We want to check now the router LSDB, LSA of this particular router 2.2.2. So RTA will go and evaluate it. So for example, if we press display OSPF LSDB router 2.2.2.2, we can be able to see the networks that have been attached. The networks that have been attached to this particular router. So we can see that it is attached to this guy. It has been attached to this guy. It also has been attached to this guy. And this is just a stubnet, so we are not going to consider it. Okay, so let's begin. Do we have an entry on our RPT on this network? 10.1.12.2? Yes, we have it. So we ignore it. We're not going to add it to the candidate list. Do we have an entry to 235.2 on our RPT? We don't have it. So we don't have it. Remember, this is where we had reached. So we don't have it. So we add it. We add it to our candidate list. Do we have an entry Of this, no, we don't have it, so we add it. After adding it, we do the total cost. So this one, total cost is 1 plus 0 plus 1. So 1 plus 0 plus 1. Where is this last one coming from? From the cost here. From the cost. Where is this 48 coming from? From the cost here, the metric. So 1 plus 0 plus 48. 1 plus 0 plus 1. So I hope that is clear. So in this case, this network has the lowest cost, and therefore it is added. It is added on the RPT. After being added on the RPT, as I said, it's simply going to be removed. After being added to the RPT, you are removed from the candidate list. Okay, so let's move on and see the next step. So now, this guy is also the DR. Remember, when we did display OSPF LSDB, we had two network LSAs, and I explained why we have two DRs, because we have elections on two network segments. So this guy is also a DR. That's why the color is like that. So now we go ahead and evaluate the network LSA of this particular DR in the next slide. Okay. Oh, it's not moving. Okay. Anyone with a question, by the way, up to there? Okay, are we good? Are we understanding? Hello?
Are we creating an SPT or an RPT?
Shortest path tree, SPT. We're creating an SPT, shortest path tree.
You've been saying RPT.
Oh, sorry. Oh, shortest path tree. RPT is what we call a rendezvous point tree, which we're going to look at much later. I'm sorry about that. So SPT. Okay, so let's move on. So RTA will go ahead and evaluate the network LSA of this particular pseudonode. See the attached routers. Anything that has already been added on the SPT will be ignored, like 2.2.2. So the entry 3.3.3 and 5.5.5 are going to be included now in the candidate list. Now, when we include 3.3.3 in the candidate list, the candidate list is going to realize that we have 3.3.3.3 again. So it's going to compare the cost. So compare the cost of that 3.3.3 and this one. So the cost of this one is going to be 1 plus 0 plus 1 plus 0 because this is a DR. So 0. Anything attached to the directly 0. So once we have that, then this 3.3.3 is going to be cancelled out. It's going to be eliminated, deleted from the candidate list, and the new 3.3 is going to be added. So after that, the two have been added, so it's going to compare the cost. This one has a cost of 49. No, we cannot add you to the SPT. This one has a cost of 2. Yes, let's see. This one also has a cost of 2. Oh, okay. So we have two nodes that have the same cost, 3.3.3.3 and 5.5.5.5. So when this happens, then both candidates are added on the SPT. So that's why you can see here, we've added 3.3.3 and 5.5.5 because they tied at the lowest total cost. Okay, so after that, we go ahead and examine. We examine the Router-LSA of 3.3 and also the Router-LSA of 5.5.5. So remember these things, it's the router that is doing this calculation. So here we are just understanding how it does it. Okay, so at number 5, step number 5 here, we're simply examining the router LSA of 3.3.3. We want to see hii 3.3.3 iko attached kwa nani na nani. So iko attached kwa hii 2. Do we have these 2 already in our RPT? 3 to 5? Yes, we already have it. So we don't need to consider it anymore. Do we have 1.1.1? Yes, we already have it. So we really don't need to add anything. We don't need to add any other thing on our candidate list. Remember, we deleted 3.3 and 5.5 from our candidate list. So that's why the only thing we're having now is 4.4.4. This one is a stubnet, so it cannot be added on the candidate list. Okay, so let's move on. So now we consider 5. This router 5. Let's look at router 5. So we look at the router LSA of router 5. So router 5 is connected to this guy who is already on our SPT. So we don't need to consider them again. It's also connected on 4. And 4 is not on our SPT. So we have to add 4. We have to add 4 in our SPT. So to add 4 on our SPT, we have to add the total cost. Yeah, E4. So it's going to be 1 plus 0 plus 1 plus, remember tuko kwa 5, plus 0, then plus 48. So that will give us 50. That will give us 50. Remember, already we had another 4. We had another 4. This other 4 is giving us 49. So because there are 2, we are going to remove the one with the highest cost. This one with the 50, we remove it. So now, after removing it, because we don't have any other candidate in the list, this is the only one, 4, we now have to add this 4, but we have to add it on the parent node. So the parent node is 2.2.2. So that's why 4 has been added here from the parent node. And the cost of that particular route is 49 total. 1 plus 0 plus 48. So that's how we add 4.4.4, not under this router, but under 2.2, because if we add it under this router, it's going to be a longer distance. So it simply means 4 has been connected to both router 2 and to router 5. If you look at the picture that you took, let me just confirm with mine. So router 4 is RTD, exactly. So RTD has been connected to both RTB and RTE. So for RTA, if it needs to go to RTD, it's better if it goes through RTB rather than going through RTE. So that is what the shortest path tree really gives us, the shortest distance from yourself to any other person in the network. Okay, so that is it. That is it about the creation of an SPT. I hope you've managed to understand some of those points. Now, after creating the SPT, the next thing is optimal route calculation. So here you pick up the routing information from LSAs of all nodes in the SPT. So routing information from all nodes. So you go node by node. You start from RTA, you go to this DR, you go to this one, you go to this one, then to this one, then to this one, then to this one. All of them routing information. So you start with the route in the same sequence as they were added to the SPT. Oh, it's important. This one is important. In the same sequence as they were added to the SPT. So that means you have to go to this one, then to this one, then now you come back to 4. So you pick any routing information from each one of them. Now, that routing information is what is going to be used to be installed on the routing table. So to get to this network, you need to use this next hop. So that is what we did there. So if you do now display OSPF routing table, you should be able to see all the destinations to each of the networks in that particular area. So we have all these networks. So they have been added from the STP. They have been added from the STP in the next phase, which we just looked at in the previous slide. So you can see that's how it's able to know the cost, what type of link is it, what's the next hop, who's the advertising router, and in which area are they. So right now, we only have what we call intra-area routes. So all of them are from area 0. In the next chapter, we're going to learn about inter-area. In the next one, we're also going to learn about external and other special OSPF areas. Now, it's important to mention that it is not OSPF. Routes that have been learned via OSPF will not always be installed in the routing table. It's not sure, but that if it's best for OSPF, then it can be installed in the routing table. Why? Because of the preference. You remember when we learned about introduction to routing, we talked of the preference value. So each protocol is associated with a certain preference value. For example, I think OSPF is 10, RIP is 100. So if we have another protocol that has a better preference, if that protocol learns about this network, then that protocol, it is what that protocol learns that is going to be installed in the routing table, and not what OSPF has learned. So the preference value will always come at play. So you know that is a question that can really come as a true or false question. So it's important that you understand that. Okay, so let's just see. You're going to do this in the lab. That is what we are breaking to do right now. So when you want to create a single area configuration, so what you do is you go to each of the router, you configure the OSPF. So OSPF 1 is the process ID, then router ID, and then you give it the router ID. As I've explained earlier, please, when you're configuring router IDs, use the router number. So if it's RTA, use 1.1.1, or RT1, use 1.1.1. Then you have to specify the area. Then after that, you advertise the networks using the network command, all the networks that you're attached to. So for example, RTA is aware of this network here and this network. RTB is aware of this network here, 12.0, 24.0, 235.0. So you advertise each one of them like that. And it's similar. So you have to do so in all the other routers. So that is how we configure OSPF. It's quite easy for a single area. So after you've configured OSPF, you can always use the command display OSPF peer brief to see the neighbors, to see your neighbors. So for example, RTA has these two neighbors. And you can also see the state, full state, means they are in full adjacency. So RTB and RTC are the neighbors via this interface. So they have been connected to that neighbor via that interface, G00, and this one via that interface on area 0. Okay. So next, can someone assist us? A volunteer with the first question, and maybe another one with the second question? Or can I be selecting someone to try? John, please try the first one. John.
Yes, I can hear you. What types of links can be described by Router-LSA? So for the types of links, there is a wait. There's just
that's right. I know it's a lot of information.
Yeah, and I'm still trying to catch up on the rest, the previous one.
Okay. Someone else can help John? What type of links can be described by Router-LSA? We have 3. That's the hint. There are 3 types of links.
We have Stubnet.
Stubnet.
Transnet.
Transnet.
And I think the other one was point to point. Yeah.
Point to point. Very true. Thank you very much, Macau. Okay. Yeah. Is Winnie here? Any of the ladies? No, they're not there. Okay. Gadudi, you can help us with the next one. I think this one I've just said right now. Will an OSPF derived route be certainly installed into a router's routing table? The answer is someone else. Gadudi is not there with us. The answer is no, right? Hello? Macau, can you hear me?
I can hear you.
Oh,
yeah,
okay. Good. So the answer is true, eh? Okay, so asanteni sana. At this point, we want to do our very first lab on intra-area OSPF configuration. So let's break and do that particular lab for the next hour and then proceed for lunch break. Asanteni sana.